In this video, we'll take an intensive look at written responses to equilibrium. So, to start with, let's think about what sort of questions you might get. So you may find you get a question which relates to what's the effect of a stress on the position of equilibrium? Now, obviously it's not going to say that, but it might say something like, what's the effect of increasing temperature on the yield of hydrogen? The increasing temperature is your stress, the yield of hydrogen is the position. Or it might be the other way around. What stress do we need to exert to cause the desired change in equilibrium position? So there you might have a question saying, well, what changes could the chemist make to increase the amount of hydrogen produced? The changes the chemist is making, they're the stresses we need to exert. The amount of H2 produced, well, that's which way does the equilibrium go? You may get some questions that relate to K values. Now, you might not realise they relate to K values, but they're ones where you've got to use K to figure out the answer. So it might ask you things like, is this system at equilibrium? The only way we can know is by saying, well, when we plug the values we've got in our question into this K expression, does it equal K? Or we could also see questions that relate to rate of reaction, some of which are also equilibrium questions. More commonly, they're just ones where people seem to think they are, but they're actually not, because they're not reading the question. Let's take a look at each of these types of questions in turn. So firstly, what is the effect of stress on the position of equilibrium? Now there's 5 steps that you need to follow here, and let's look at it in an example. So here is our example. It's an endothermic reaction where we've got the steam reformation of methane. Okay? Hydrogen's one of our products. So the question would be, if the volume of the equilibrium system is increased, what happens to the yield of the hydrogen? So our first step is to define what the stress is and its direction. So our stress in this case is increasing the volume, which will decrease the pressure. Okay? Change in pressure is the stress, the direction is the decrease. Then we're going to have to describe the immediate impact. So if we increase the volume of everything, we decrease the concentration of all reactants and products. That's our immediate product. That's our immediate impact. Step 3, how's my system going to compensate? What's it going to do about it? Well, to partially compensate, always partially remember, for the decrease in pressure, we're going to favour the forward reaction. Fourthly, why? Very important. You can't just say it's going to go that way. You can't just say because of Le Chatelier's principle. You've got to show that you understand Le Chatelier's principle. And the reason here is because there are more gas particles on the right of the equation than the left. You probably want to throw in the ratio. It's a 2-to-4 ratio. And then finally, make sure you actually answer the question. So the question asks, what's going to happen to the yield of hydrogen? You've got to state that impact. So the yield of hydrogen will increase. Yes, okay, you might think it's implied in the previous steps. Implied is not enough. You have to state it. If we flip it around, and we think about questions we're asking us, what stress do we exert to cause the desired change? Okay, then stick with the same equilibrium system. Remember, it's endothermic. If we're asked, what temperature should a chemist operate this system at to maximise the yield of H2? The first thing we're going to do is we're going to look at the equation and we're going to discuss it in relation to the condition. So what in this equation tells us something about temperature? Well, it's that very last bit, it's the delta H. We have to state this reaction is endothermic. Then, define the direction the system has to move to have the desired effect. Okay? So it tells us we want to maximise the yield of H2. So to maximise the yield of H2, we need a net forward reaction. And yes, I know this should be a double-headed arrow, but it's not. Deal with it. Okay? Then we've got to link the two. So what change in temperature will favour that net forward reaction? Okay? So in this case, because it's endothermic, we're going to say an increase in temperature will favour the net forward reaction. And fourthly, why? And again, do not just say because of Le Chatelier's principle. You've got to explain it. So because this will, going in a forward direction, this will cause heat to be absorbed from the environment, which partially opposes the temperature increase that you imposed on the system. Okay, third type of question. Okay. So, might be something with K values. the K is going to be in the question somewhere, or maybe you even calculate it in a previous step. In the question, they'll also give you some data, which will say that's what the concentrations are currently. So, same equilibrium system. Here's our K value at 400 degrees Kelvin. If these are the concentrations measured, which way is the equilibrium system going to move to reach equilibrium? Now, it's not necessarily going to be that explicit. These numbers might be buried somewhere in a big block of text. You've got to search for them. But if it's asking you which way is the system going to move to reach equilibrium, you've got to be comparing K to what values we get now, okay? Which is our current concentration fraction, which is CF, or sometimes capital Q. This is measured, calculated in exactly the same way as you calculate K. So we plug in these values, the concentrations that we've currently got, and we get a value. Okay? And this should have units. The units technically should be m squared. Then we compare this value to K. Okay? So step 1, we calculate this. Step 2, we compare it to the K value. This is a bigger number than that. Okay? Which means that we've got fewer products at equilibrium than there should be. Okay? No, it means we've got more at equilibrium than we should have. I've just realised I've made a mistake here. I'm sure you all picked up on it. CF is bigger than K. K, of course, is calculated by products over reactants. So if CF is bigger, then there are more products that present than there should be at equilibrium. So the reaction will proceed in a backwards direction to reduce the amount of products. My apologies there. Everyone makes mistakes. These last 2 steps should be reversed. Finally, questions relating to rate. So you may see a question which is combined equilibrium and rate. Okay? If something increases the rate of a reaction, it increases the rate of all reactions, including those that are at equilibrium. So if we increase temperature, increase concentration, increase pressure by decreasing the volume, if we add a catalyst, all of those always increase the rate. So most of the time, if you are asked a question and it says what happens to the rate of the reaction, you ignore the fact that it's an equilibrium system. And you just answer it as a rate of reaction question, because that's what they're actually asking. Okay? The only exception to that is if their question is separately asking you what happens to the rate of the forward and the backward reaction. In which case you've got to think about the graphs, and you've got to think about, well, which one is going to increase in rate more than the other? Because that's what's going to cause the change in position of equilibrium. So if you're getting a net forward reaction, then your forward reaction is going to initially increase more than the backwards, and then until they reach their new equilibrium where they're both at the same rate again.